Ever wondered how your phone charges wirelessly or how motors spin? It's not magic, it's physics. Today, we're revealing the invisible forces behind almost every piece of tech, electricity, and magnetism. These two are inseparable, governed by a few key rules that unlock how our world works. We'll break down 4 fundamental laws of electromagnetism with real-world examples and animations. By the end, you'll see electricity and magnetism everywhere you look. Let's dive in. Meet Ampere, a brilliant French physicist whose curiosity about electricity and magnetism changed the world forever. In the early 1800s, he was fascinated by the mysterious forces that seemed to act at a distance, invisible yet powerful. Ampere discovered that every electric current, no matter how small, creates a magnetic field around it. No exceptions. This was a revolutionary idea at the time, revealing a hidden connection between electricity and magnetism. Picture a simple wire. If there's no current flowing, there's no magnetic field, just an ordinary piece of metal, silent and still. But the moment you add an electric current, something amazing happens. A magnetic field instantly wraps itself around the wire, forming invisible loops of force. The stronger the current, the more intense the magnetic field becomes. It's like turning up the volume on an invisible force that surrounds the wire. This principle is the secret behind powerful electromagnets, used in cranes to lift cars, in scrapyards to sort metal, and even in the tiny speakers inside your headphones. To figure out which way the magnetic field circles the wire, scientists use the right-hand rule. Point your thumb in the direction of the current, and your fingers curl in the direction of the magnetic field lines. If you reverse the current, flip your hand. The magnetic field reverses too. This simple trick helps us visualize the invisible. Thanks to Ampere's law and the right-hand rule, engineers can design electric motors and generators, predicting how these invisible forces will act and harnessing them to do real work. So Ampere's law tells us, wherever there's current, there's magnetism. The right-hand rule shows us the direction, making the unseen world of electromagnetism visible and understandable. This discovery was the first real bridge between electricity and magnetism, uniting them into one powerful force, electromagnetism, that shapes our modern world. From the power lines above our heads to the devices in our pockets, Ampere's law is the foundation of how our world is powered. Let's keep going and see where this force leads us next. Now let's talk circuits. Circuits are the highways for electricity, guiding the flow of energy through all our devices, from the simplest flashlight to the most advanced computers. Understanding how electricity moves is key to unlocking the secrets of modern technology. Imagine electricity as cars on a road, zipping along wires like vehicles on city streets. Just as traffic follows rules to avoid chaos, electricity obeys its own set of laws to keep everything running smoothly. That's where Kirchhoff comes in. He gave us 2 fundamental rules, current law and voltage law, that help us predict and control how electricity behaves in any circuit, no matter how simple or complex. The current law says that what flows into a junction must flow out. No electricity is lost or magically appears. It's like water splitting into pipes. The total flow in always equals the total flow out, keeping everything balanced. The voltage law tells us that in any closed loop, the total voltage gains and drops always add up to 0. Think of it as a round trip. Whatever energy you gain from a battery, you must use up in the circuit before returning to where you started. Batteries provide the push, resistors and bulbs use up that energy, and the loop balances out perfectly. This balance is what keeps your devices working safely and efficiently. Thanks to Kirchhoff's laws, engineers can analyze even the most complex circuits, whether it's the tiny chips in your phone or the massive processors in a supercomputer. These rules are the foundation of electrical engineering. By turning chaos into order, these laws make modern electronics possible, powering everything from city lights to the devices we use every day. That's Kirchhoff's laws, simple, powerful, and absolutely essential for understanding how electricity shapes our world. Lenz's law is all about resistance to change. Think of it like a stubborn teenager who just doesn't want to go along with what's happening around them. No matter what you try, they push back, refusing to be influenced easily. When a changing magnetic field induces a current in a coil, that current isn't just a passive bystander. It creates its own magnetic field, and that new field always acts to oppose the original change. It's like the coil is saying, "Not so fast," to any magnetic disturbance. Push a magnet into a coil, the coil pushes back, resisting your efforts. It's almost as if the coil is actively protesting, making you work harder to get that magnet in. Pull it out, the coil tries to pull it back in, clinging to the change and refusing to let go without a fight. The opposition is always there, no matter which way you move the magnet. You have to do work to overcome this opposition, and that work doesn't just disappear. It gets transformed into electrical energy, powering devices or lighting up bulbs. The harder you push, the more energy you generate. Lenz's law ensures energy is always conserved. No free electricity, no shortcuts. Every bit of energy you put in is accounted for, keeping the universe's books balanced. This principle powers the technology all around us. Transformers that send electricity across cities, induction cooktops that heat your food, and even the magnetic brakes that safely slow down roller coasters. It's nature's way of keeping things balanced, making sure that for every action, there's an equal and opposite reaction, and nothing is ever wasted. Lenz's law, always fighting change, always conserving energy, and always making sure the universe plays fair. Faraday's law is the key to generating electricity. It says, a changing magnetic field inside a coil induces a voltage. No change, no electricity. Move the magnet and you get current. The faster the change, the more voltage you get. More loops in the coil, more voltage too. This is how power plants work. Turbines spin magnets and coils, creating electricity for our homes. Every time you plug in a device, you're using Faraday's law. It's the elegant principle that turns motion into power. Faraday's law, the engine behind our electrified world. Let's wrap up. You've just unlocked the secrets of Ampere's law, Kirchhoff's laws, Lenz's law, and Faraday's law. These aren't just theories, they're the foundation of every electric and magnetic device you use. Now you know how motors spin, why transformers work, and how we generate electricity. Next time you charge your phone or flip a switch, remember the physics at play. Keep exploring, stay curious, and see the world with new eyes. Thanks for watching Science Simplified. Like, share, and subscribe for more awesome science videos.